Hi, this is the first video in our Fourier series, video series. And so first, before moving into what is Fourier series, let's discuss where does Fourier series comes from. So the best place to start discussing about Fourier series is the Euler's equation. So this is the Euler's equation, and as you can see, this is quite interesting because there are exponentials, imaginary numbers, cosines, sinusoids. So all these mathematical concepts are being compressed into one equation, and this has like we can say this has simply changed the course of mathematics. And so this is the Euler's equation. I am planning to make another video on how to prove Euler's equation using uh, Taylor series, and let's see. But for now, this is the Euler's equation, and this is going to be quite important when we move ahead, when we go ahead in Fourier series. And the most important concept, so Fourier series is essentially about rotations and periodicity. And before moving into rotations, let's discuss on how uh, what we call this rotations can be defined in mathematics. So the easiest way we can explain what rotation is by using complex numbers. And uh, so we define the unit circle on the complex plane. So unit circle means it is centered at the origin and the radius is unit 1, unit 1. And so that gives us the unit circle, and this is going to be the basis of all the rotations, because like uh, rotations can be very different, but like if we want to define another type of rotation, we can simply increase or decrease the radius, so that essentially scales up or down our rotations. And so next we want to define a point on the unit circle. So this is, here I have defined it as P, and this uh, this notation, so as you can see, it is omega, uh, it is turned omega from the real axis, and it is lying on the unit circle, so it is away 1 unit away from the origin. And as a result, here this is known as the like polar coordinates. We are using an angle and a distance, how much we turn from the real axis and how much we move away from the origin. And so next we will move into Cartesian coordinates. And before moving into Cartesian coordinates, we will check what are the projections this point make onto the x-axis and the y-axis. So the x-axis means the real axis, when y-axis means the imaginary axis. And as you can see here, the projection onto the real axis is cos omega, and projection onto the imaginary axis is sin omega. So using these projections, we can write this point P in Cartesian coordinates like this. So this is the standard imaginary numbers, complex number notation. And as you can see now, this is quite familiar from the Euler's equation we discussed earlier. And so actually this is essentially the Euler's equation. And yes, so this is, now we have used Euler's equation to simplify a point on the unit circle, and this is it. And so now, rather than taking a fixed omega, a fixed angle, we can make it dependent on time. So omega is a function of time, and as a result the point P also becomes a function of time. And you can show it like this. Since omega is a function of time, both projections, cos omega and sin omega, both the projection onto the real axis and the imaginary axis, both of them also become functions of time, as you can see here. So these projections being functions of time is very important, and we will discuss it in a later video. And so how are we going to define this function omega t? For simplicity, we will define it as a like having a constant angular velocity, because omega is a function, omega is the angle, is an angle, and when it becomes a function of time, we can define the angular velocity. And angular velocity is essentially how much you turn in a given time. So we will take it as a constant value. So omega t is going to be a function with a constant angular velocity. And as a result, both the sine and cosine functions, both the projection functions are also going to become functions with constant angular velocity. And so we can visualize this very beautifully, and I will show it to you here. As you can see, when the rod or the point, so actually speaking here, the point is turning in the other direction, so minus omega t, and when the point is moving along the circumference, when the point is moving on the uh, unit circle, it creates two projections, and those two projections are also functions of time. They change when the time goes on, time moves forward. And that's it, and that is it for this video. Thank you so much.